that's good. Anyway, hopefully it won't be too boring. So I'll be talking about read once algebraic branching programs. This is joint work with Raz and Shpilka. So before, since I guess maybe many of you would know the introduction already, I'll just tell you the theorem we're going to prove and then introduce it later. So we're going to have a field which is polynomially large in these parameters n, d, and r. And I'm going to say that there's going to be an explicit set curly h of points of d vectors, and it's going to be quasi-polynomially large, such that for any function f, which is computed as follows, you have d matrices a1 up to ad, and each ai is an r by r matrix of univariate polynomials. So each entry will be a univariate polynomial in the relevant variables. So ai will depend on xi, and you take this product of matrices, and then you take the sort of the 1, 1 entry. And so suppose f is computed by such a polynomial, and say it's degree n, then f will be the identically zero polynomial if and only if it will be identically zero on all of these points. So this is where we want to go. And throughout this talk, the field will be polynomially large. I'll just stop saying that. So H is the hitting set. Yeah. Yeah. So this is black box polynomial identity testing, quasi-polynomial-time. All right. So just to review this question on motivation as to why I'm talking about these things.
You said the A sub i's were matrices.
That's right. So yeah, so it's an r by r matrix, and each entry in the matrix is going to be a polynomial.
Okay.
And so you multiply these matrices, and you get a matrix. So I'll give an example later. Quasi-polynomially large. So log d is the number of variables here. Yeah. So the reason it's d is because this is an ABP and it's depth d and I don't know, it's not Okay. So the PIT question is, given a polynomial, is it identically zero? And when we say given, we mean that it's given by a small computational device. I give you this device. You want to say, does this device compute the zero polynomial? And as an example, we can have this formula, computing x squared minus y squared. And there are many models of computation here. There's formulas where this sort of computation structure is a tree, where you have multiplication gates and addition gates internally. There's also obviously a circuit also where you can have sort of a directed acyclic graph. We're going to be talking about something called an algebraic branching program, which I'll define shortly, and that'll be the focus of this talk. We're not going to be talking about general ABPs. There's a read once variety, which again, I'll also define. All right. So there's this lemma by Schwartz-Zippel that says that if you have a non-zero polynomial and you evaluate it at a random point, it will be non-zero. And for the students of history, there's this DeMillo-Lipton also there. Yeah. So this gives you a randomized algorithm for testing if the polynomial is zero by saying that if you're given the polynomial, just evaluate on random points, and that will, with high probability, be correct. And this usually only uses f as a black box in the sense we're given this computational device, but we're only using it to evaluate it on chosen points. A white box algorithm can also be interesting, and this is sort of one where you can really exploit the structure of the circuit that you're given to decide if this is computing the zero polynomial or not, looking at the way the circuit is wired. As was pointed out, this work is really about black box algorithms, but white box are also interesting, and there's prior work that works in the white box model. Right. Yeah. I mean, we believe what black box exists, and obviously black box is white box. So the probabilistic method, as usual, says that if you're given a computationally simple f, like an f given by a small circuit, then there exists some small set h such that f is zero if and only if f on h is zero. And so this is really saying that there exist small hitting sets for the set of small circuits. The main question is, are there explicit such h? And that's sort of where we're going with this talk, constructing such things. And so this h is called the hitting set. And it turns out that these black box algorithms are basically the same as hitting sets. And so I'll just mostly be talking about hitting sets. All right. And so there are various reasons for being interested in this, and one is that this is sort of the frontier of de-randomization. It's sort of related to, in the Boolean world, constructing these pseudorandom generators for restricted circuit classes like constant depth circuits, things like this. So if you're interested in pseudorandomness, I mean, for some reason this is important. But there's other reasons, and one is this sort of diagram, right? So if you want to talk about algebraic circuits, you can first talk about lower bounds. And lower bounds, it's saying we just want an explicit function that cannot be computed by small circuits. And then, of course, in this landscape, there's also the white box PIT algorithm. You're given this circuit, does it compute the zero polynomial? And you're allowed to sort of look at the circuit. And then there's black box. And in some cases, there's some notion that if you get good enough lower bounds and you really understand circuits well enough, then with some hard work, you can get to white box. And then in some cases, with even more hard work, you can get to black box. And this is sort of a circle because you can actually go back from black box to lower bounds, do this connection of Heinz, Schnorr, and Agarwal. And there are sort of other connections in this diagram. Obviously, a black box implies a white box. Perhaps more surprisingly, you can go from lower bounds to black box. So Kabinets and Poly also gave the first such reduction, and then Dviershvil and Yehudev gave such a thing for constant depth circuits. And there's also another arrow going sort of this way, which is a little bit weaker. So even though there's some notion that this is just a question of pseudorandomness, there's also this very nice connection with lower bounds. And so maybe if we do this, we can sort of use these nice, there's sort of this direction, and maybe we can also use this direction, possibly. But that, of course, requires us to get such things. OK, so this is polynomial identity testing. And there's obviously a lot of prior work. So Agarwal-Vinay showed that black box PIT of circuits can be reduced to the depth 4 case. And basically this is saying that the depth 4 case is potentially very difficult. So maybe we should try sort of smaller restricted classes. And consequently, there's a lot of attention on these restricted classes. So one is depth 2 circuits, which is sparse polynomials, sort of the easiest case. So there's we have black box PIT results for this. There's depth 3 sigma pi sigma k circuits, sort of bounded top Bannon, which I won't be talking at all about. A lot of work there. Constant read formula. More relevant for this talk is the model of non-commutative or set multilinear algebraic branching programs. And so there's this white box algorithm for PIT due to Raz and Shpilka. And there's sort of some partial black box results. There's a prior work of Amir and myself, and some later work, Steer, which I'll mention later. And so there's sort of these white box things, but not really great black box results, in contrast to some of these other cases where we really have sort of a tight understanding, like relationship between, if we have a white box, then there's a black box, which is vaguely similar. And so the motivation of this work is sort of looking at this case and getting stronger black box results. Yeah. So there is a formal statement there that I didn't really want to talk about, but basically it's how to put it best. Basically, if you can do this in if you can do depth 4 circuits in polynomial time, then you can get general circuits in quasi-polynomial time.
But you need to do the black box for that for really large ones that are really
Yeah, right.
ones that are exponential that much.
Right. So, yeah, I mean, I'm trying to be formal, but there's things there. Yeah.
Actually, the order of this was not quite that. So I guess
Yeah.
the real Shpilka paper was first. The Agarwal-Vinay explained why even
Right.
that 3 is different.
Right.
That's all good.
Yeah, so this is a little revisionist. Obviously, you can tell the dates. OK, so as I mentioned, this work is about black box PIT of these read once oblivious algebraic branching programs, which is a bit of a mouthful. I'll say ROABP, which is even still a mouthful. And one of the reasons that this work considers this model is that in some sense it efficiently captures other models which were previously interesting. So one is that it does in fact capture a sparse polynomial. So if a function is computable by is a sparse polynomial, then it has a small read once algebraic branching program. And in particular, this is important because it says that any function can be computed by this ROABP, maybe not efficiently, but can be done. In some sense, non-commutative ABPs reduced to this ROABPs. Even though these are commutative and these are non-commutative, there's in some sense, in this work we actually give a reduction, which I'm not going to talk about. But there is a white box algorithm for doing PIT of this non-commutative model given by Raz and Shpilka. And this work actually gives a black box by this connection. Diagonal depth.
This is a fully polynomial.
Right. Yeah. So the white box algorithm is fully polynomial. This work will give quasi-polynomial black box results. Yeah. So there's this diagonal depth 4 circuit model, which was defined by Saxena, and he gave a white box algorithm basically by reducing to the Raz-Shpilka algorithm. And because of this connection, we can also sort of show that diagonal depth 4 circuits are captured also by this ROVP model. There's also some independent black box results by Agrawal, Saha, Saxena earlier this year.
Just for the diagonal depth.
Yeah. Yeah, so they showed bounded depth pure formulas or something. So there's also this depth 3 set multilinear model, which sort of can be seen as a tensor. And there's, again, by reduction to the non-commutative model, there's a white box polynomial time algorithm for PIT by Raz and Shpilka, and some quasi-polynomial black box results. One is previous work with Amir, and then also this Agrawal Saxena paper. All right, so in some sense, this ROBP model captures a lot what was done before in some sense, but in some sense, it has an independent, So there's also this recent paper of Momoli showing that de-randomizing nether normalization can be reduced to PIT, and Amir and I have some partial progress showing that what Momoli really needs is PIT for this read once model. So even in, say, pure mathematics, there's some motivation. Yeah, so after you talked to Peter on Friday, Peter and I,
Normally have some consequences of
Right.
deterministic identity testing. Some
Right.
even very strong consequences.
Right.
But you can do it. You do it white box, black box, you can do it.
Right.
So that's what about all these consequences.
So I think the consequences are not quite as drastic as what Momoli would suggest, but we can talk about that.
You have a deterministic algorithm testing multiple consequences. This
Yeah. Yeah, I believe, so, okay, this is partial work towards this, and we can talk about it afterwards. Yeah, but I think that, Momoli gave a reduction to PIT, and I think if you do this reduction a little bit differently, you get read once ABPs. For what it's worth. Okay. So there's also some notion that there's been a lot of work in Boolean pseudorandomness, and one of the really nice results there is pseudorandomness for small space computation. And in small space computation, the device they're looking at is this read once branching program. And this is sort of the RL versus L question. And basically, they have ROBP, and we're just inserting an A in there, right? So this is some sort of algebraic analog. And this is actually a fruitful idea to think about this way, because if you look at what we're doing later on, you'll see that our results follow some of the paradigms established earlier in the Boolean world. So there's some notion that because of this, there's some motivation, and also they capture other results. Okay, so now actually I want to define what this is. So a polynomial is computed by depth d, degree n, width r, ROEP, if R are these polynomial matrices. So each matrix is R by R and has entries which are polynomials, such that F is the 1-1 entry of this multiplication. And as an example, to make this more concrete, is that we can have this bivariate function xy, and we take two matrices. The first one depends on x, the second one depends on y. You do the multiplication, and you get some polynomial. And for people who are more accustomed to branching programs as graphs, you can say this does correspond to some graph. It's this layered directed acyclic graph, where the way this graph computes is that you look at all ST paths, and the reason that S and T are distinguished is because we're taking the 1-1 entry. You look at all ST paths, and you sum the weights of these paths. The weight of a path is just the product of the weights on the edges. So this top path would be this edge, this weight times this weight, and there are only two paths. So this is a way, you know, an algebraic branching program computes. The reason it's read once is because in this layered model, we read x once and then we read y once, and we don't come back to any of these variables. If we allowed you to come back to a variable, then you'd have a much more powerful model, but we don't know how to do any lower bounds in that case. Yeah, so throughout this work, I was going to talk about that later, but basically I'm assuming that this variable order is known, that you always will read x1 first, then you'll read x2, and so on. And this is sort of a complicated notion because in the white box model, you can kind of just identify what that order is. In the black box model, our work will assume you know the variable ordering. And this is sort of the same case as with, say, like the Boolean world, where you sort of need to know the order of the variables. Our work will not work if you don't know the order.
The PRGs are much weaker when you don't know the order.
Right. So in the Boolean, yeah, I mean, there's recent, right.
Versus,
Right. So yeah, this recent Fox paper. So this is, you can think of this as a non-commutative model because you're always multiplying in the same order. But you can also think of this as a commutative model, right? Because you know, there's no need to ever reorder any of the multiplications.
What it's asking is whether you will use
no. Yeah, we won't be using. So in the previous work on tensors, we used commutativity, and sort of the reason that this work took some work was because we couldn't do that anymore. So yeah, and this model in some sense captures non-commutative ABPs through a reduction, which we can talk about offline if you want. So white box, there's this algorithm of Ron and Amir that you can do it in polynomial time. And this will be black box. And one of the difficulties is that what does it mean to do for doing black box PIT for non-commutative models? Because you can't evaluate over a field anymore because the field is commutative. And so the right notion is you evaluate this black box ABP over matrices. And you want to have a small collection of matrices that if this ABP is zero or non-zero, it will evaluate to some non-zero point on this matrix evaluation. Okay. So there's this picture again with lower bounds, white box, black box. And again, there's this notion that you can go forward. Unfortunately, the lower bounds don't really imply black box PIT directly because of these connections don't work in these limited restricted models. So you really have to kind of go forward in this circle. And we can kind of do that. So Nisan in 91 gave strong lower bounds for ROBPs. I mean, he gave it in this non-commutative model, which is much more general, but you can read it this way. So very strong lower bounds. And then Ron and Amir gave this white box PIT algorithm with some hard work. And what this work is doing is saying, let's just do more hard work and get a black box PIT algorithm. Of course, this is quasi-polynomial, where this is polynomial. So we're losing something. And the sort of thing that's really underlying all of this is the method of partial derivatives. And I want to talk about that now, explain it. So concisely, it's just partial derivatives are a complexity measure, and that gives you lower bounds. Less concisely, you can say, let S be a set of vectors, and you're going to take all partial derivatives of F in this set. So you just look at all partial derivatives, but only some set of partial derivatives. And a lot of works, like these, will do the following. They'll take some circuit class C, say like the set of small branching programs. They'll come up with a set of vectors, and they'll say that if F is computed in this model, then these sets of partial derivatives have small rank. And the point is that this is in fact a vector space. It's just the vector space of all polynomials. Then they'll find some explicit function that has large rank, and then conclude that this is we have a lower bound. So this is a lower bound technique, but you can actually use this for polynomial identity testing. And I'll talk about this, how you actually, what Nisan did, for example, in his lower bounds. So that if we know the variable ordering, then you can take the derivatives sort of x1 up to xi. So you're only taking derivatives of the left half of the variables. And Nisan showed something roughly, I'm kind of lying, saying that if you only take these derivatives, then and f is computed by a small ABP, then the rank of the partial derivatives is about lower than the width.
When you say derivatives, actually you mean all derivatives, not just first derivative.
Yes.
But all derivatives.
Yes. Right. Yeah. So take all derivatives of all combinations of the left variables, and that space will be smaller than the width of the ABP computing f. And so, if you look at the space and the space is large, then it must need large width, needs a large ABP.
You maximize that.
Yeah, you can do that. Or you can just, you can do it.
It actually gives the characterization. I mean,
Right.
you think it will be maximizing P over 2 or like the determinant.
Right.
But he actually takes all of that and then he gets this as
Yeah. So he in fact gives very an exact characterization. And one way of thinking about this, which is slightly, I guess, maybe non-standard, is you can kind of think of this as a two-player algebraic communication game, where in some sense I hold the left half of the variables, you hold the right half of the variables. We're communicating via the ABP, and if you think about communication, complexity, and rank, maybe it's not surprising that this relation sort of holds. Okay. And one way of what Ron and Amir did is they said, we're going to use this as follows. So suppose you fully expanded the ABP in the monomial basis. Obviously, that would be an exponentially many monomials. But let's do it one variable at a time. So you have x1 and x2, and you're going to expand all of the x1, x2 terms all the way on the left, because you're sort of reading in variable order. Then when you do this, when you add this new variable to this expansion, you can sort of change bases to reduce back to this rank bound. In the sense that if you did this expansion fully, you get exponentially many terms, but you sort of expand and then change basis into a much smaller space. And you can do that because there's sort of low rank things going on. So you do some Gaussian elimination, and then you add a new variable, reduce to the rank, and so on. And at the end, you'll sort of expand all of the variables and get something which is 0 if and only if the original thing is 0.
So the basis will be roughly what's generated at some cut of the function.
Right, right, right. Right.
So that's the reason for the small ranks.
Yeah. Yeah.
You remember only
Right.
the one.
Right. Yeah. And so what this work is doing is it's sort of taking what Ron and Amir did and just moving it sort of to the black box. So it's kind of hard to explain at this point. We're going to do a change of basis in a black box way. And what I mean by that is that to do a change of basis with explicit polynomials, you say use Gaussian elimination. But obviously, you can't do Gaussian elimination to a matrix you don't know. So we need to do that in a black box way. And we're going to do that by using a seeded rank extractor. And each iteration, or each time we do this change of basis, we need a new seed. And to actually get a good result, we need to do this in parallel. And that's the proof in 2 lines. So now I actually want to just state the main theorem again in case you forgot it. So I'm going to state it slightly differently. I'm going to talk about a polynomial map, where it's mapping log d variables to d variables such that if f is computed by a small ABP, then f is 0 if and only if f on g is 0. And a way to think about this is it's sort of like a PRG in the sense that g is indistinguishable from fresh variables by any small ABP. G itself is computed by a small ABP, so it's very explicit. And G has small degree. And the way you get back to the hitting set is you just sort of fully interpolate these variables, these log d variables, and each of these has polynomial degree, so it's sort of polynomial to log d.
What was your condition?
It's polynomially large, so it's polynomial in n, d, and r. So it can't, at least that much. So it's any characteristic is that, yeah. So as I said, this is sort of some algebraic analog of a pseudorandom generator. In some sense, it's sort of vaguely similar to what Nisan and INW did for small space. And as was mentioned, this generator or these hitting sets really depend on you knowing the variable order. You can't do it. Yeah. And that's as Blinkist. All right, so now I want to tell the proof idea. So the main thing is how to merge 2 variables into one. And in the sense that you have x and y, and I want to replace x and y with one variable z. And the main question is how do you do that? And we're going to use a rank extractor, and I'll show you how to do that. But once you kind of get this step, the way we're going to do this happens to have that this uses a seed, and there's only a small number of bad values for this seed.
So it's no longer appear into adjacent matrix.
Yes.
You are doing matrix multiplication
Right.
to adjacent matrix.
Right.
But,
Right. Yeah. So you'll merge adjacent variables into one, and then you can kind of induct from the bottom. Right. And because so they'll be adjacent, and there's a small number of bad seeds, and by a union bound, you can merge d over 2 pairs of variables at once. So you can merge all adjacent pairs of variables, and you're only going to use one seed for all of the merging, so this is sort of in parallel. And because of the union bound, you don't have that many bad values. So this step goes from d variables to d over 2, and then you can kind of just recurse. And we get log d rounds. This is why it means we're doing it in parallel. And we're only using log d seeds. And then the remaining one variable will have small degree. And each seed has a small number of bad values, so you just sort of you interpolate the last variable, try all seeds, and there's only this many values to actually try. And that kind of gives you the hitting set. You can unwind this to get the generator, but I'm not going to talk about that.
the degree, when you multiply the 1, you are replacing these two matrices with one.
Right.
The degree of the polynomial
They'll increase but very mildly. Like in some sense, it'll be n, and then it'll go to 2n, and 3n, and 4n when you do this. But yeah. So it definitely right. So. Oh yeah. Okay. So yeah, the total degree of these things will always be bounded by d n r to the 4th. So you'll never. But it really be 2, 4, 8 because you're doing it that way. But as we'll see, the degree blow-up will actually be kind of a problem we'll have to overcome. So I want to talk about how to merge variables because this is sort of an amorphous concept. And you want to basically, what does that mean? It makes you're replacing these two variables with one, and you're preserving some property of your function. But what properties do we preserve? Clearly, we want to preserve non-zeroness of the function, but maybe that's enough, maybe it's not enough. The first idea is to use Kronecker substitution, which basically says that if you have low-degree functions, and I'm using low degree to say that, or small letters to say these are just polynomials. Capital letters will be matrices. That if these are degree n, then there's some notion that you can replace y with x to the n, and everything's the same. And especially there's a bijection between the monomials, and so in some sense we have merged variables. But what's wrong with this is that this squares the degree, right? We went from degree n in each of these variables to degree n squared, and that's a problem because after log d rounds we get n to the d degree, and this is way too much. And in some sense you would expect this because we haven't used anything about the fact that this is computed by a small AVP or anything. Okay. So a second attempt is just to say let's preserve non-zeroness recursively, right? Because we have a read once AVP, which means we'll do everything on x and then we'll do everything on y. So maybe we could preserve the non-zeroness of x, preserve the non-zeroness of y. But that's not going to be good enough either. It's not strong enough in the sense that if you have a of x is this matrix and b of y is this matrix, then if you just replace x with y, you'll get both of these matrices being 0, but when you multiply the matrices, you get 0. So we need to do something stronger than just preserve non-zeroness independently. And what we're going to do is we're going to preserve the span of each polynomial matrix separately. And to do that, I need to define what I mean. So suppose you have a set of matrices curly A. We're going to define this matrix span of A to be the span of all matrices in A. And if you have a polynomial matrix, so A is a polynomial it's a matrix with polynomial entries, then the matrix span will just be the span of its coefficients. And this is what I want to preserve throughout the recursion. And one important thing to note is that the rank of A over like the function field, which can only be up to R, but this matrix span can be up to R squared.
But sorry, what are you trying to preserve here? So it's so in the matrix polynomial version,
Right.
it's for each I, you're just looking at the coefficients in A that are of x to the I, and you're trying to preserve the span of that matrix.
Like, yeah, if you have a bunch of multiplications, a bunch of matrices, you're going to preserve the span of each one of them independently. And then you're going to sort of merge variables, preserving. So if you have two polynomial matrices, so I'll give an example in the next slide.
Just that in our space,
Yeah.
if you plug one
So yeah, so A of x is a matrix of polynomials, right? And so apply this coefficient operator entry-wise.
So for each entry,
You-
remove all the terms that do not involve xi and
Right.
Yeah, another way of thinking about it is just write the matrix itself as a polynomial.
Right.
A0 x to the 0 plus A1 x to the first. And you're just taking the
Right.
coefficient.
Right. So yeah, you can either think of it as a matrix with polynomial entries, or you can think of it a polynomial with matrix coefficients, and then you can get this result. This
It's
definition.
just the same as substituting and evaluating.
Right. So that's my
Okay.
next bullet. Okay. Yeah.
Steve, what does it mean span of xy? I mean, is it the union of the all lines?
So
It's
y-
a collection of matrices, and it's a span. Also, it's vector
Oh,
space. I see.
Yeah.
It's a vector space of matrices. What we want.
Right.
So we take the span of the union of all the columns.
Yeah. Yeah, and Swastik pointed out, because of polynomial interpolation, this is just the same thing as the span of the evaluations, because the field is polynomially large. And we'll use both of these, both the coefficient and the evaluation. And we're going to say that A is approximately B if their spans are the same. And the important point is that preserving the matrix span preserves the non-zeroness, just because the span is 0 if and only if the polynomial itself is 0. Okay, to be a little more, okay. So the reason this is important is because of the following lemma. It's that if you have 4 collections of matrices and A and A prime have the same span, B and B prime have the same span, then A dot B and B has the same span as A prime dot B prime. And what I'm saying is that this is A dot B is just all matrices in A times all matrices in B. And so this is saying that you can recurse properly because you just, if you have such a product, you can preserve the left hand, preserve the right hand, and then you've preserved the entire span. So the proof of this is very simple. It's just matrix multiplication is bilinear. Sort of just do it.
Go back like that.
Yeah.
Okay, so here we're not talking about the equality in dimensions, but actually set is the same in equality of matrix spans.
Yeah. So when I say matrix spans are equal, I'm really saying that, yeah, the span of these things is equal. Okay. And so the idea is that we're just going to recursively preserve the span on, let's say, the left-hand side, the right-hand side. This will preserve the span of everything, in particular preserves non-zeroness. Yeah, so now more concretely. So let's consider now capital F, which is just the product of the matrices. So we're not taking the 1-1 entry. If we preserve the span of this will preserve the non-zeroness of the 1-1 entry, right? And so suppose that we break F into the left-hand side, the right-hand side. You know, this has, say, d over 2 variables. This has d over 2 variables. If we can replace each of these d over 2 variables with a new single variable, such that the matrix spans are equal, then by the lemma, we'll get that the matrix span of F is the same as the matrix span of this bivariate polynomial. So we've reduced, say, d over 2, or d variables to 2 variables, you know, recursively. And this is true even though, you know, we've reduced many variables. And so we do this by induction. But then the question is, how do we actually do the inductive step going from 2 variables to 1 variable?
And expression, if we consider the example before the one that makes this, we can preserve each of their non-zeroness, but we don't preserve the product.
Right.
But wouldn't you have the same?
Right. So that's
Just replace y with x there, it preserves the span.
no. So if you do that, you've correlated them in a bad way in some sense. I mean, the reason that you need to merge variables so the main thing is that the span preservation lemma like really gives you there's no mouse. Okay. Lose mouse. So the span preservation lemma really gives you this lemma here. Really gives you that you can preserve these things independently. And the reason that that example doesn't work is basically saying that you merged x and y inappropriately. You should have merged them in some other way.
Yeah, I'm just trying to see what goes on, and it seems that if you replace y with x, the span of b remains the same.
So the span remains the same, but you haven't merged them in a good way. Like I haven't made any claims about merging yet. I'm just saying if you have this.
You know, A and A prime. We don't mix the A's and the B's. Here, A has the same span as A prime. B has the same span as B prime. In this example, you would like something on the left to have the same span as the X matrix. On the right, to have the same span as the Y matrix. Instead of Y, span involves Y.
Yes, but okay, you can understand correctly the span, when you do the span, you just take the coefficients of the y.
So, but this lemma is about you still have two formal variables.
Right.
Because you have the variables for the A and you have the variables for the B.
But the matrix span removes the variables.
No.
No. So
It's really,
oh, it leaves the variables.
it leaves the variables. It's a condition. It's like a pre-processing condition for what he's now going to tell us about how to merge them.
Right.
Right.
Yeah.
So span is defined for not just primitive,
Yeah. Span will also be defined actually for arbitrary polynomials, which is not.
Support over the image of all possibilities with a pair of formal variables. Right?
Yeah. Yeah. So what will basically happen is this says I can preserve the span of left, preserve the span of the right, and now I can look at the span of just A dot B, and I want to preserve the span of this thing. So I want to go from A dot B to just A prime or something, right? And that's the merging step.
I'm sorry,
At
could you
most
go back?
points, it's really good because you have to be careful when you define a span. It's not just a vector space or let's say all evaluations. Then the variable disappears and it's not statistic.
I'm sorry, could you go back one slide again?
Okay.
Okay, so
Yeah.
when you write the coefficients of xi, you mean that you leave, you take all the coefficients of xy with xi?
No.
So,
no.
so in the span,
So yeah. Okay. You can preserve.
there is no xi, there are no variables.
Right, but the point is that with the merging example that went wrong is that you're not preserving the span. Like you have A of x and B of y, and then you can consider the span of A of x times B of y. Like that is one matrix. It happens to be bivariate. Just take the span of that, and you didn't preserve the span of that.
But your lemma says that they don't need to span.
No, this is the lemma is only if you don't merge variables at all.
The lemma hasn't presented a solution for that problem yet.
Yeah.
So that problem, the problem was that it was an incorrect merge. So what he's giving is just symmetries that, other products that you can consider that if you can preserve those, you'll still preserve it.
Yeah.
What I'm saying is that if I'm taking the methods that he had before
Yep.
with the y, and they take the span of them, you will have exactly the same span as if I just replaced y with x.
I
in the
agree.
same method.
But the lemma he's asserting on the next slide is not about, so you have the product of A and B there, or B prime and B, or, the other combinations, right? The formal variables in A are x, and the formal variables in B are y.
Right.
So the resulting product that you get is all possible matrices you get from ranging x and y over all of space.
Yeah. So I haven't.
See, what goes wrong in the other example is the fact that he's tried to merge variables.
Yeah. So I haven't mixed like this implicitly. Yeah. Implicitly assumes that I haven't mixed any variables. No variables have been merged yet.
This table is basically A and B. The
Yep.
A's and the B's are
Different variable.
Oh,
These are matrix. No,
I
so
see.
polynomial involving distinct variables. The A matrices and the B matrices will not exist in this line. In this line.
In this
I
line.
see. Okay.
Okay. So yeah. So I haven't. Yeah. So let's talk about now how we actually get. Right.
This slide.
Yeah.
So I'm a little lost on the introduction. Zero subscripts.
Just left. I broke up the d variables into like left variables and right variables, and so zero.
Right after that, so it's the first half of that.
Yeah. Yeah.
I mean, all he's saying here is he needs to tell us how to merge two variables
Right.
into one.
Right.
And then we'll get something about it.
Yeah. Okay. So now let's actually do that. So the main construction is something called span preserving curves. So think of alpha as a constant, but these are polynomials in alpha as well, such that for any a of x and b of y of low degree, we want that a of x ax by, that the matrix span of this, where you say either take over all coefficients of x to the I, y to the j, or look at all evaluations, the matrix span of this polynomial is, this bivariate is the same matrix span as this univariate. And this is true except for polynomially many alpha. And it's important to contrast this with the Kronecker substitution. This is saying that these curves have degree polynomial in R, whereas the Kronecker substitution would actually have degree, say, this would just be z and z to the n. And if you had these degree depending on n, you get a really bad degree blow up again. And so the fact that you can do it with R is the magic, I guess. Alpha we'll think of as a constant, but we're basically saying that for every a and x, a and b, there's only a small number of bad alpha. Right.
The right-hand side is a matrix whose entries are held as a constant univariate polynomial.
Yeah,
Right.
that's right, but you're looking at the span.
Oh, the span. Oh,
Really, that means that they're the same.
Yeah.
Yeah, just that the span is.
Right. Right.
B alpha is a function of alpha.
And z. It's a function of alpha and z.
Polynomial function of alpha.
That's right.
And the degree.
The degree in both of them is small, but I'm sort of trying to think of alpha as a constant because it's sort of the seed to this extractor. For all n? What do you, yeah, I mean it's. Yeah, p and q. Yeah, I guess they're dependent. Are they? So no. It only depends on R. They only depend on. Okay. Okay, so this is what I want to show, and of course the Kronecker substitution has no seed. This has a seed. It's its own problem. But now I want to show how we're going to use this to actually get a generator.
Wait, so that seems surprising, though, that as Andy was asking, I mean, so you're taking the degree in the polynomial, the degree n, and the polynomial entries of a and b respectively.
Right.
Would be, arbitrarily large.
Okay, so yeah, there is one part of p alpha and q alpha which will depend on n.
How many bad entries there are, or something, or?
No, like there's a constant in these that you need to have high multiplicative order. The multiplicative order needs to be at least n.
It's just a field.
It-
It's
the
just
field,
this part.
yeah.
It's not about
But it's not about the yeah, right. That's true. Right.
I see, yeah, so for example, if you take one matrix with just degree n entries inside, the span of that vector space of matrices can't be more than R squared.
Right. Right.
I see.
Yeah. So the intuition is that, yeah, I mean, there's not really that whole lot of information going on here, so it's sort of polynomial in R. So we're really reducing to polynomial in R. So I want to say how I actually get the generator from this. If we have A, B, C, and D on 4 variables, we can apply the curves independently on A and B and C and D. And by a union bound, we can find one alpha that works for all of them. And then by applying this lemma on span preservation, we can say that we take these 4 variables. We can, on the left, change them to a single variable x prime. So we'll put in the curves there. On the right, we can merge these 2 variables to one variable and put in the curves there. And now we have a bivariate problem, and we can do the thing again and say, well, we're going to merge these two into a new variable using another set of curves with a new seed.
So this is where you use this lemma span preservation.
Yeah, really that we're doing this in parallel.
Oh, right. So it
Yeah.
is used when the variables are the same.
Yeah, right. Yeah,
Just like in the Nisan generator, you can think of the alphas and betas as the alpha.
right,
Very few ones will do that.
right,
I understand the analogy, just want to understand
Right.
where you use this.
right. Yeah. So that's really all where I'm using that lemma. And so now we plug it in, and we've reduced 4 variables to one variable, and then we can just fully interpolate, the alpha, beta, and x prime, and that will be our generator. Okay, so if we have these curves, we do get a generator. The problem is that in general, what's going to happen is you're going to have xi as this composition of curves, and the degree is going to be quasi-polynomial, and there's sort of a feedback loop going on that not only is this interpolation costly at the end, this affects the number of bad seeds you can have, and then you get sort of a polynomial to log squared. So not only is it not low degree as a generator, you get a worse hitting set. So in some sense, even though this seems inherent as this composition method, but we'll actually show that you can avoid this by sort of opening up the span preserving curves and understanding them a little bit better. So now I want to tell you how we make these curves. So we're going to use a seeded Vandermonde, yeah. Right. Yeah.
Not necessarily. I mean, so
not
what if it's z squared or something?
Yeah. No, z squared should be fine.
Oh, okay.
So if you think of the matrix span as evaluations, as long as the polynomial has, sufficiently many evaluations, then yes. Because the matrix span, generically, yeah, you will preserve it. That's right. All right, so we're going to use a seeded rank extractor, which is Vandermonde-like, so we can't use any rank extractor, but there's two such things, Gabazon and Raz, and then Amir and myself gave a small improvement to this. And it says the following. Suppose you have an element of multiplicative order, which is high, and you have some single matrix A, which is degree n, and the matrix span of A, which is the span of n coefficients, is the same as the span of r squared many evaluations to these carefully chosen points, omega to the L times alpha. And this will be true except for nr squared values of alpha. So in some sense, this is surprising because it's saying this on the left-hand side is sort of the span of n things, and on the right-hand side, it's the span of just r squared things. But it's not too surprising because really this is just an r squared dimensional vector space. So we're just sort of, if n is really, really large, we're just sort of shrinking it down to what it should be. Okay, and it's important for our composition that this only depends on r, otherwise we get some sort of blow up. All right, and to tell you how this is roughly proven, recall a rank extractor. A rank extractor says that for any matrix and for most values of the seed, the rank of E alpha m is equal to the rank of m. Pictorially, we have some tall. No, I'm going to tell you more or less what it's going to be. But yeah, so m is this tall, thin matrix where the rank is sort of lying somewhere. And we're going to extract it into this much smaller matrix using this function E alpha. And the way Amir and I did it, just a small parameter improvement, is that this row here will be the moment curve of omega to the L alpha, which means that in the jth column, you have omega to the L alpha all to the j. So that fully defines the matrix, where L goes from 1 to whatever. And the way we're going to use this is that the jth row in this matrix here will be the coefficient of x to the j in aj. More specifically, you can write ax as this polynomial with matrix coefficients, and this will just be aj flattened as an r squared dimensional vector. And as such, there'll be r squared many columns, and there will be n rows, one for each coefficient. So I'm not going to prove to you why this is a rank extractor, but hopefully you'll trust me. But when you do this multiplication, you can say, what is the lth row of the output? It will just be a at omega to the L alpha as an r squared dimensional vector, and you can just sort of do it out. And why is this important? Well, by definition, the row span of this matrix is contained in the row span of this matrix. Because they are the same, you in fact get that the row span of these two matrices is the same. And then you sort of look at it. Well, this matrix this is just this is a at this evaluation. And so the row span of this thing is simply the span of these evaluations. And if you look at m, well, these are just the coefficients of a. So by definition, this is the matrix span of ax. So whenever the seed actually works, you get that the span of the evaluations is the span of the matrix. So this is, all right, so let's go from this extractor to the curves. So the curves we're trying to do preserve the span like this. And what we're going to do is we're going to interpolate curves such that this sort of path in two-dimensional space passes through these points, where now I'm taking L and L prime to be independent from 1 to r squared. And there are r to the fourth many of these points, and so if you kind of think of alpha at least as a constant, this says that the degree in Z should be at most r to the fourth, because it's just linear algebra. This is many constraints, so I need at least this degree, and that suffices. And once you have these small curves, you can say, well, we have A and B. Then for most alpha, from the rank extractor lemma, we know that A of x, the span of A is the span of the evaluations, and same for B. Then it follows from independent span preservation that the span of AB is the span of the multiplication of the evaluations, where you're taking L and L prime to be independent. And then these curves will pass through those points. So then the span of AB is the span of AB at the curves, because these things pass through all of these matrices, and you can't violate anything by just plugging in evaluations.
So one thing that was the issue when you had this span preservation.
Yeah.
I mean, there was a bivariate thing. I'm not studying bivariate.
Well, just like curly A and curly B, or?
This thing, yeah, you said you had A of x was A prime.
Right.
Y was B prime.
Right, so that's what I'm doing here. So this is A, curly A, and this is sort of curly A prime. And this is B and curly B prime. And I'm just sort of then multiplying them together to get this line.
But then you said that it only works if the variables are disjoint.
Don't say the A and N prime is not defined.
Yeah.
Oh.
So that's why I phrased it in terms of this with language of just sets of matrices, because there are no variables in this case. But on the right there's a variable, but the matrix span is just the span of the coefficients or something. Okay. Right. So basically I took a hitting set in some sense and then made a generator out of it. Yeah. And that's important because before I didn't have any variables, but now I have a variable, and now I can recurse. So using these span preservation, these curves, as before, this gives us a quasi-polynomial degree generator. And now I want to talk briefly about how do we avoid this blow-up, this degree blow-up, because that seems kind of interesting. So if we start with 4 variables and we merge to 2, so now we replaced it once with the curves. Well, let's think about what would happen next. What would happen next is you would actually say that this span is actually the same as when you evaluate you replace x prime with omega to the k beta with the new seed, and you replace z prime with omega to the k prime beta, where the k and k prime are independent. So you're using the rank extractor independently on the left and the right. And now we have a set of point. So this is saying this span is the same thing as this. And the interesting thing is, instead of treating these curves as sort of generic, you can think of them as now defining new points. So you can consider p alpha on omega to the k beta. And now you have only r to the fourth points. So you're going to take 4 new curves, like pp, qp, and so whatever, that are going to depend on alpha and beta, that are going to pass through these curves. So I took this point here and just put it here. And I want these curves to pass through these points. And again, there's only r to the fourth many things, so each of these curves will be degree r to the 4. And then you can replace these points with these curves, and you've gone from 4 variables to 2 variables. Okay. And then generally, this is different, because before what would happen is I would say I want curves going through these points alone, and introduce a new variable, and then you have this composition problem that the degree would blow up. But now, okay, it's not a bad one, but yeah, right. Yeah. So then basically, when you do this process, you're always going to go down back to degree r to the 4th curves, and this also plays nice with the alpha I that I'm really thinking. In this presentation, I've said the alphas are constant, but everything is polynomial and no division. Okay, so this gives us, you go back down to degree R4 or the fourth curves, you just do all this induction, and you get the main theorem, basically, that there's this map that fools small RVPs, which gives you your hitting set. This generator itself is actually computed by a small read once ABP, which I didn't talk about, and then the degree is small because of this nice composition. The way we did it is we used this rank extractor to preserve the matrix span at chosen points, and then we passed curves through these points. And then we always got this low degreeness because of the way we did composition. And because the overall span is maintained because of this independent span preservation lemma, we get that it's 0 if and only if the original thing was 0. And we interpolate all of the variables, get all seeds, and then we're finished. Okay. So some conclusion. Yeah.
So if you just treat the polynomial map from F to the polynomial map, a random polynomial map with polynomial around.
It should be. I believe so, yes. But just in the sense that like a random polynomial map should have sort of a random image on some level, and then a random image should be a hitting set. Yeah, I think so. Right. Right. Yeah. Right. Yeah. Yeah. So I mean, hopefully, we would want to get this to be, constant. This log d to be a constant. Because basically, the log d is where we're getting this quasi-polynomial, because it's just polynomial to the log d, and if you got polynomial to the 1, then it'd be polynomial. Okay. So some conclusions. I didn't show you, but we give reductions from diagonal circuits and non-commutative AVPs in the black box model to PIT of this RVP. So we get quasi-polynomial black box PIT for these things. We got this black box version of this partial derivative method, which has been fairly successful. So maybe this will be interesting for other reasons. And we get this quasi-polynomial hitting set. And applying it, we get, for these other things, we already knew such things for tensors, but we get it again. Diagonal circuits and non-commutative. Yeah, I was trying to avoid that. So I guess I don't know where the partial derivatives are in the partial derivative method on some level, but basically, to me, it's more just it's a rank-based method that you're splitting variables, you're looking at a matrix and saying this has a low-dimensional space. More or less, the partial derivative method is because you look at the space of partial derivatives in a certain sense, and that was low rank. But I don't have a great answer to that question. Where?
If you do it in the non-commutative program, then what you're looking at, you look at the left and the right half, and basically you look at the middle layer where you have the only outer is the outer dimension. But then the partial derivative is the left half. It's just partial derivative.
Yeah, yeah. Right. Yeah. So we get this, analog of the Boolean generators for RL. There are obviously some open problems. The proof of what we did is sort of very similar to previous works in the Boolean case. We do recursion. We have extractors. I don't know if there are formal connections. Maybe there are. Maybe there aren't.
So, is it conceivable, let's say you take your generator,
Right. Right. Could be. I guess there's this weird thing though, right? Like that, which I don't know how to handle. That in the Boolean case, when you talk about hitting sets or generators, you're always saying, well, this branching program already accepts 30% of its inputs, and you just want to find one input that it hits. Here, you know, we sort of syntactically know that already that just by being a non-zero polynomial, fraction are non-zero. And I don't know how to, I mean, that's the canonical, sorry? Yeah, yeah, so that's like the canonical, like the promise versus non-promise issue. That,
But it's quite likely that what Mike said will still work. You start
right,
with the Boolean matching program and you do it with the clear through.
right,
Program and you just know that it doesn't always reject.
right.
So over the Boolean doesn't always reject, which would mean that it will
Just like the polynomial.
accept, yeah. Just like, yeah, may work with maybe even alternative.
The one actually thing that I was hiding is that the fan out is different in the sense that usually for space S Boolean stuff you have 2 to the S width, whereas here, and that's because, you know, the fan out of every node is 2 in the Boolean case. Here the fan out can be arbitrary, and that actually plays not that well with the parameters.
But that's not true. In Nisan generator, you immediately move to looking at
Okay.
of long and variables at a time, which means it's polynomial fan out, just like in calculus.
Okay, that's
But
true.
That's what it really amplifies.
Okay, right. But there is the issue that, I mean, there, you know, if you have 2 to the S width branching program, then the hitting set will be, no, I guess that's 2 to, okay, yeah, I think you're right.
If you could use this pseudorandomness generator for doing the Boolean thing, you get a different area.
No, because this is quasi-polynomial. So
It really corresponds to this general.
yeah, you get the same sort of log squared behavior.
Here you map loci variables to
It's because of this degree. If this was constant, I would agree with you. But basically, because this is polynomial degree, you get the polynomial to the log,
oh, I see.
and that's where the quasi-polynomial happens.
Does that mean if you improve the exponent from log D, you would also improve your D's for
Potentially, yeah. Potentially, I mean, there could be some transfer of results, but not formally at the moment.
oh, it's not something that's immediate.
Not immediate, no. I mean, just everything is similar in spirit, and that's lots of spirited people, but not enough formal connections. All right, so the, you know, open problems, this connection, this generator only works for fixed variable ordering. There's been some nice recent work in the Boolean case for generators for arbitrary orderings, but we're far from optimal. It'd be nice. Maybe we could get better seed lengths, you know, simpler subclasses, we don't know. Anyways, okay, that's it. Thanks. Right. 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 From what I know and understand, I mean, maybe Mike can say more, is that, you know, this is really looking at the program in some way, and it's not actually like that result is not actually a PRG, right? So maybe you can get an analog of that, but I don't know.
Maybe
Might convert the black box.
Right. Right.
a more related thing is maybe doing the constant width like in Raz.
Right.
The constant width is better than
Right. Right.
square, but it's
Yeah, I mean, we've thought a little bit about it, but not too hard. I mean, what restrictions can you get that? I mean, there's obviously constant width. There's these, you know, permutation branching programs, things like this. Can you get better results for that? It's unclear.
So your pseudorandomness generator, very analogous to the Nisan generator, will work in, does it also give you an analog of the eigenvalue generator?
I mean, you can debate which it's closer to. I don't know. I mean, I don't know. Oh yeah, I haven't thought about those things. That's right, right. Yeah, I haven't thought about those. Those seem hard. Yeah, I would like to know, but that's a hard question.